Hi everyone, I'm Siddharth. I'm a second-year PhD student at Purdue University, and I'm here to present our work, ARGUS, a framework for stage static taint analysis of GitHub workflows and actions. So what exactly are GitHub workflows? So GitHub Actions is a CI/CD platform that is developed by GitHub and released in 2018. So it has various features that make it very popular among developers. The platform allows developers to define workflows which can automate development tasks. So these workflows can use actions, which are basically applications that perform commonly repeated tasks. Workflows are event-driven, which means that they can execute based on triggers such as pushing code, opening issues, etc. So our goal in this paper is to try to identify command injection vulnerabilities that are present in GitHub Actions. So now let's take a look at a sample vulnerable workflow. So now if you look at the bash command that's being executed, it's basically trying to echo the issue title. Now, when a user creates an issue on the repository, so it's going to end up printing the title. However, this can be used by an attacker in a malicious way when he creates an issue with a malicious title, such as the one here, which basically ends up executing commands on the runner. Now, since the last talks were about Rust, they didn't give an introduction about workflows. So I'm going to do the introduction about workflows. So on the top of the workflows, you can see the triggers. So these are triggers which determine which events the workflow is going to execute on. Then you have jobs. Jobs are basically independent tasks that are being run. And each job has a set of steps that will get executed sequentially. And because these jobs and steps are independent, to communicate between them, you can use basically output variables and environment variables. Finally, jobs also have dependencies, so a job waits until all its dependent jobs finish execution before it runs. And event data is a way for workflows to access data such as pull request titles, etc. So now introducing two more features of our actions. So GitHub workflows basically run with access to a GitHub token, which allows it to interact with GitHub API, such as committing code, creating issues, etc. Now, since these permissions are dangerous, GitHub provides a mechanism to restrict them, such as the workflow here is used to deploy content to pages. So the workflow only needs to have read-only access to the contents of the repository. However, it needs to have write access to the pages scope. Another important functionality is called encrypted secrets. So this feature allows you to store key value pairs for like sensitive information, such as API keys, SSH private keys, and store them in the workflow. So the example here shows a developer trying to clone a private repository. So he needs to authenticate it using an SSH private key. So based on OWASP guidelines for secure CI/CD pipelines, we defined a threat model. So in our threat model, an attacker should not be able to execute arbitrary commands in the pipeline without corresponding code changes. Attacker should not be able to gain unauthorized read-write access to the repository or any of its associated scopes. The attacker also should not be able to exfiltrate any of these confidential secrets that are stored in the pipeline. So thinking about all of these factors, we come up with 4 major challenges that make it hard for any existing system to find vulnerabilities in GitHub workflows. So the system must be aware of the workflow semantics and the execution flow of the workflow. The system should also be able to track data flow from workflows into reusable workflows and actions used within these workflows. The system should also be able to support multiple programming languages that are used here, such as Bash, JavaScript, Python, YAML, etc. And finally, the system should also be able to predict the potential impact of such a vulnerability. So to solve all of these challenges, we designed our system, ARGUS, which is basically a stage static taint analysis tool to identify command injection vulnerabilities in GitHub workflows and actions. Now let's take a look at the design of ARGUS. So in the first stage, ARGUS runs a taint analysis on all the GitHub actions that need to be analyzed and generate taint summaries for each of this action and then store them in the taint summary database. Then we convert each workflow into a WIR, which is basically a custom intermediate representation that we created for representing CI/CD pipelines. Then we run the static taint analysis engine on the workflow IR, which basically queries the database for taint summaries whenever needed. Finally, whatever reports that we get, we run the impact classifier to classify the impact of each of those reports. Now let's look at each of those components a bit more in detail. So for the first step, for generating Taint summaries in Actions, we basically try to develop plugins to handle each type of action. So there are 3 major types of actions. The first type is JavaScript actions, where the functionality is usually developed within using Node.js. The second type is composite actions, which are basically YAML files with syntax similar to workflows. And the third type is basically Docker actions, which are pre-built Docker containers. So our tool currently supports both JavaScript and composite actions. In the IR generation phase, we try to capture various features of the workflow, such as the order of execution, the execution environment, including the type of the action, or is it a bash command, arguments, environment variables, and the special CI variables and where they are referred. Now, to run the taint analysis and propagate the taint, we also create a workflow dependency graph. The workflow dependency graph maps the dependencies between jobs inside a workflow, and if a workflow has a job which contains a reusable workflow, it merges the graph of the reusable workflow into the main graph. And finally, coming to the impact classifier. So there is a diverse impact based on the vulnerability. So we classify them into 3 types: high, medium, and low. Let's look a bit more detail into each of these. So the high impact vulnerability are vulnerabilities where the attacker can exploit these vulnerabilities and then use them to leak a GitHub token with write permissions or maybe some confidential secret that the developer had in the workflow. These allows the attacker to basically either commit code back into the repository or misuse those secrets. So an example is basically a workflow that runs on issue creation. So the attacker can simply open an issue and run the workflow and exfiltrate secrets. Medium impact vulnerabilities have the same access to the GitHub token and secrets. However, they require some sort of maintainer interaction for the exploit to run. Assume a workflow runs on a push event. So the attacker needs to open a pull request, the maintainer needs to accept the pull request, and then the workflow will run and the attacker can exfiltrate secrets. And the low impact vulnerabilities are workflows where there is no access to a read-write GitHub token or secrets. So for example, on pull request event, GitHub automatically reduces the permissions of the GitHub token, and it does not pass secrets, so the attacker cannot exfiltrate these. So now let's look at an interesting vulnerability that we discovered. So ARGUS found a high impact vulnerability in one of the popular open source repositories called Dynamo, which has over 1,500 stars. Now let's look at the vulnerable workflow. So as you can see here, the workflow is set to run on the creation of issues. And it does not define any permissions, which means that it will when the workflow runs, it has access to secrets as well as a read-write GitHub token. So it also defines a job named redirect issue. Now let's look into the job. So in the first step of the job, you can see that it's checking out the code. And in the second step, you can see that it's setting the environment variable issue title as the title of the issue. Now this environment variable is again used in the same step as a parameter to an action. Now ARGUS, when it encounters an action, it tries to go to the taint summary database. And in the taint summary database, it notices that the taint from the variable input string flows into an output named replaced. Now in the very next step, you can see that the output replaced is actually being used in a bash command. So this basically causes a command injection vulnerability. So how can an attacker exploit this? In the very next step, you can see that there is a secret Dynamo bot token, which the attacker can exfiltrate using this vulnerability. So for the evaluation, we majorly focus on 4 points: the accuracy and precision of our taint tracking on actions, workflows, and the effectiveness of ARGUS in identifying security vulnerabilities. And finally, we do a comparative evaluation with the current state of our tools. We created 2 data sets for the evaluation. Our real-world data set contains 2.8 million workflows, 1 million repositories. And we also created another data set, Workbench, which has 24 previously known vulnerable workflows. As you can see, among these, there are around 48,000 actions, out of which we were able to analyze around 70%. Now, when we talk about taint analysis on actions, we can classify them as two types. The first type is input flow, where the input originates from inside the action. It gets the input from the workflow, and it flows into a sink inside the action. Direct flow is where the taint originates from the action. It directly accesses the API parameters, and it flows to a sink inside the workflow. So any action that has direct flow vulnerability causes any workflow that uses it to be vulnerable. So we evaluated the precision of ARGUS on these actions. We found out that we had a 94% precision on JavaScript actions, 96% on composite actions, and we found 80 unique direct flow actions that cause any workflow using them to be vulnerable. For taint analysis on workflows, we identified 27,000 vulnerable workflows, including all of the workflows in the Workbench, and ARGUS classified 3,600 of them as high impact. Now, because we cannot manually verify all of these vulnerabilities, we sampled around 5,000 of them, and we verified that we have a 93% precision in finding these bugs, and we found almost 5,000 zero-day vulnerabilities. So for the comparative evaluation, we compared against two other tools, one by the GitHub security team itself and another paper. And we almost got 7 times more vulnerabilities than them while keeping a good precision. So because we had all of these vulnerabilities, we didn't really know how to report these vulnerabilities. So we reached out to the GitHub security lab, who validated all our findings and helped us plan out the disclosure procedure. So they also published a blog post about our research. Due to their help, we were able to coordinate with developers to fix over 150 workflows and around 20 actions, and we got around 20 CVEs from these. And that's it with my talk. Thank you for attending. I'll take any questions.